Modern commercial vessels are floating mountains of steel. A fully loaded container ship can weigh hundreds of thousands of tons, yet it glides across the ocean surface without sinking. The physics that keep that steel afloat are absolute and unyielding. It comes down to Archimedes' law, the golden rule of floatation. A floating ship must displace a volume of water that weighs exactly the same as the total weight of the ship itself. This diagram illustrates that exact state of equilibrium. You have two competing vertical vectors, the downward force of gravity, marked here pushing down from above, and the upward force of buoyancy, pushing back from below. The downward force is the total mass of the ship and everything inside it. The upward buoyant force is the mass of the fluid that the hull is physically pushing out of the way. If you load more cargo, the gravity vector increases. To balance the equation, the ship must sink deeper to displace more water, thereby increasing the buoyancy vector. This creates a constant mathematical tension for marine engineers. A ship is a dynamic environment. As fuel is burned and cargo is loaded or discharged, the downward mass changes. Simultaneously, as the ship travels across the globe, the density of the ocean water changes, altering the upward buoyant force. If a deck officer cannot accurately calculate this shifting equation of displacement, they cannot predict the ship's draft, the vertical distance from the waterline to the bottom of the keel. Miscalculate the ship's draft, and you lose the clearance needed to keep the hull off the seafloor. To understand how this works in practice, we start with a strict baseline: freshwater. Freshwater has a density of exactly 1,000 kilograms per cubic meter. In freshwater, 1 cubic meter of displaced volume yields exactly 1 ton of upward buoyant force. This image presents a theoretical experiment with 3 distinct bodies. Each block has an identical mass of 5 tons, meaning each exerts the same downward gravity force. However, their volumes vary: 10 cubic meters, 5 cubic meters, and 4 cubic meters. According to the golden rule, for any of these blocks to float, it must displace exactly 5 tons of fresh water. This diagram shows the outcome for the first body. With a total volume of 10 cubic meters, it has double the required displacement capacity. It only needs to submerge half its body, 5 cubic meters, to push aside 5 tons of water, achieving perfect equilibrium. Here is the second body. Its volume is exactly 5 cubic meters. Because volume matches mass, the entire body must submerge to displace the necessary 5 tons of water. It becomes neutrally buoyant, with its top surface resting flush with the waterline. The third body, however, only has 4 cubic meters of total volume. Even if completely submerged, it can only physically displace 4 tons of water. This final diagram captures the failure point. The 5-ton downward force of gravity overpowers the maximum 4-ton upward force of buoyancy. The block is negatively buoyant. Flotation is a strict mass balance equation. If an object lacks the physical volume required to displace its own mass in water, it sinks. Calculating volume is simple for a perfect box: length times breadth times draft. But real ships are not boxes. Their hulls are curved at the bow and stern for hydrodynamics. Using the box formula on a curved hull drastically overestimates the actual underwater volume. To correct this, naval architects use the block coefficient, or CB. The block coefficient is a mathematical bridge that accounts for the empty space between a perfect rectangular block and the curved hull of the ship that sits inside it. Specifically, it is the exact ratio of the ship's actual underwater volume compared to the volume of the geometric block it occupies. The value of CB depends entirely on the ship's design. A perfectly square barge has a block coefficient of 1.0, meaning it fills 100% of the block. A standard cargo ship might have a CB of 0.7, filling 70% of the block. A sharp, narrow destroyer might have a CB of just 0.5. By factoring this in, the true volume equation becomes length times breadth times draft multiplied by the block coefficient. Once you have that accurate underwater volume, you multiply it by the density of the water to find the ship's total displacement, or weight. The block coefficient allows officers to reduce complex, three-dimensional hull curves into a single, reliable percentage, keeping displacement calculations exact. When a ship is tied up at a terminal, Cargo operations move fast. Deck officers don't have time to recalculate the entire underwater volume. They need a shortcut to determine exactly how much the draft will change per unit of weight added. That shortcut is a metric called tons per centimeter, or TPC. This animation highlights the waterplane area. TPC represents the cargo weight required to sink the vessel by precisely 1 centimeter at this waterplane. You take the area, multiply by density, and divide by 100. That flat 1 centimeter wafer dictates the sinkage rate. In practice, to find out how far the ship will sink during loading, you simply take the total weight of the loaded cargo and divide it by the ship's TPC. If your barge has a calculated TPC of 7.2 and you load 180 tons of cargo, you divide 180 by 7.2. The result is 25. The barge will sink exactly 25 centimeters deeper into the water. TPC provides a direct, linear relationship between cargo weight and hull safety, allowing officers to monitor their draft in real time. The final test of these variables occurs when a ship changes environments. Consider a barge sitting at a draft of 2.75 meters in a freshwater river, where the density is 1.000. It now departs the river and sails into the open ocean, where the saltwater density is 1.025. We know the total weight of the barge, let's say 1,800 tons, remains completely static. No cargo or fuel is added or removed during the transit. The only variable changing is the fluid. Saltwater is denser. With more mass per cubic meter, it pushes upward with greater buoyant force. Because the water is denser, the hull doesn't need to displace as much of it. The ship requires less underwater volume to balance its 1,800 tons against the buoyant force of the sea. To find exactly where the new waterline will sit, officers use the ratio rule. The new draft equals the old draft, multiplied by the old density divided by the new density. This split-screen comparison shows the math in action. We take the river draft of 2.75 meters and multiply it by 1.000 divided by the sea density of 1.025. The result is 2.68 meters. Without discharging a single ton of cargo, the physical draft decreases. The ship rises 7 centimeters up out of the water solely because it entered a denser environment. A floating ship is never truly at rest. By calculating the constant interplay between Archimedes' displacement, the geometric block coefficient, and shifting fluid densities, mariners maintain precise control over their vessels across every ocean on the planet.